will be presenting our project today, which uses the amazing population level CVD COVID UK data resource to understand the relative incidences of major arterial and venous thrombotic events compared with people without the diagnosis. So this project is led by Will, Jonathan, and Angela, who brought together this interdisciplinary team from Bristol, Cambridge, Edinburgh, Swansea, and UCL. These are listed in alphabetical order. No one is more loved than anything. So Hoda will be presenting the Welsh results and I will be presenting the English results, and the plan is to combine these using meta-analysis. So to set the scene, clinically, SARS-CoV-2 brings about a pro-thrombotic and pro-inflammatory state that may increase the risk of serious major thrombotic disorders. So we're here to investigate the relative risks of these events up to a year after COVID-19 diagnosis compared with people without. The effects of, we also look into the effects of accounting for potential confounding factors and the variations by demographic factors, as well as the history of events. So the data resource gives us 45 million adults registered with the GP and alive on the 1st of January 2020. And out of that, we get 1.4 million COVID-19 diagnoses. The cohorts followed up for a year, as we mentioned just now, up to the 7th of December 2020, which is when the UK vaccination program rolled out. So from the modeling side, we use Cox regression models, where the primary timeline is calendar time. And we calculated the hazard ratios for time since diagnosis of COVID-19, categorized as the absence of a diagnosis, which is the reference level, and then in increasing weeks since diagnosis. So for computational efficiency, because we have a huge data set, we use random sampling with inverse probability weighting for people who are not cases and or not exposed, as seen in this little figure over here. We also fitted differently adjusted models to look into the effects of accounting for potential confounding factors. So we fitted an adjusted model, which is like crude, and also age-sex region adjusted model, as well as a maximally adjusted model, which controlled for this whole bunch of available potential confounders. Of course, there might still be unmeasured and residual confounding left. We also did a bunch of subgroup analyses, which looked at how risks differed by key demographic characteristics. And that includes hospitalized versus non-hospitalized COVID, with or without a history of arterial or venous events, ethnicity, and their sex, as well as age groups, really. We also did some meta-analysis to pull together the hazard ratios from different subgroups to generate overall hazard ratios, which you will see later in our results. And a more detailed protocol can be found on our project GitHub, so feel free to check it out. So for this project, we needed a definition of a COVID-19 diagnosis and its severity, which we defined as two classes, which is hospitalized or not hospitalized. And this is based off of the wonderful phenotyping work done by the UCL team. The pictures are here. And hospitalized COVID is defined as a hospital admission record with confirmed COVID-19 diagnosis in the primary position within 28 days of the first COVID-19 diagnosis. So of the 1.4 million COVID diagnoses that we have, 0.1 million had hospitalized COVID-19. Now onto the results. The left panel here on will always be for any arterial event. So it's made up of AMI, ischemic stroke, and other non-stroke, non-MI kind of arterial events. And the right panel will always be for any venous events. So PE, DVT, ICVT, PVT, and venous thrombosis at other sites. So here you see a higher relative risk of vascular events following COVID-19 diagnosis. For arterial events, it's like 4 times higher in the first 1 to 2 weeks after a COVID-19 diagnosis, which quickly drops to 2 around week 4, and then lives there for until the end of the follow-up. You see that maximal adjustment, which is the darker line, attenuates the HRs, but it does not kill off this long-term high risk at all. So for venous events on the right, you see similar pattern with a higher long-term risk as well. You also see this little blip around 4 to 6 weeks, which has just actually hypothesized that's due to discharge from ICU to normal hospital, and they have their respective coding practices. So the spike in HR right after COVID diagnosis in week 1 might be in part due to reverse causality, so we need to be a bit careful about that. Hospitalized versus non-hospitalized. So hospitalized COVID-19 seems to give generally higher hazard ratios. For arterial events, you see they're marginally higher even in the long term. For venous events, you also see higher HRs, but mainly in the slightly shorter term, so prior to week 26, for example. Now, prior history is a bit, maybe a bit surprising. So it's interestingly, for both arterial and venous events, the adjusted hazard ratios are greater in those with no prior history of event compared to those with a prior history. Ethnicity-wise, for arterial events, the Black ethnicity seems to have a higher hazard ratio compared to the white ethnicity, with around 2 at 28 weeks versus the 1.5 for the white ethnicity. And for venous events, this time it's the Asian ethnicity that has a higher hazard ratio at 4 at the 28-week mark versus the 2.5 for the white ethnicity. Now over to Hoda for the Welsh results.
Thank you, Sam. So, hi everyone. I'm going to give a very quick overview of the Welsh analysis in 3 slides. As you see, we have used data sources held within the same data bank to create this study cohort, and this figure is a very simplified version of the data preparation process in SAIL, and full image is available to access on Miro for all consortium members. So in any theory, we would have raw data sources here shown at blue layer on top. In layer 1, we have defined population spine called COVID-19 cohort, which includes all individuals alive and living in Wales on 1st January 2020 with follow-up through multiple data sources until end of 2023 as data becomes available. This cohort also includes all Welsh residents who moved into Wales or are born in Wales after 1st January 2020. Then we have created subset of data sources only for those individuals in their population spine. These are called VMCT version of data sources. At the next layer, layer 2, we have created the phenotype tables, for example, for COVID-19 phenotype in hospital data or primary care data. And as much as possible, we use same phenotype code list for across data sources in each nation. For example, the phenotype code list used for hospital data, dispensing data, and mortality data were exactly the same as those in the English analysis. However, there were some cases where we needed to diverge from source. For example, for primary care data, we have used the read codes as this data source is coded in read in set. Finally, we arrive at layer 3, project-specific layer, where all table names and column names are exactly the same as the English version and so are harmonized. Therefore, any analytical pipeline developed in the English theory as source is reproducible with minimal changes in the English theory. There were some challenges in harmonizing data, and I'm happy to discuss them later if there was a question. Next slide, please. So this table shows baseline characteristics of Welsh population, which exactly matches on table 1 from the English analysis. Among 2.6 million individuals, there were 12,000 hospitalized with COVID and 66,000 were not hospitalized. Another point to mention here is that in addition to harmonizing table names and the columns, we have used same values for all variables. For example, for ethnicity, deprivation, or smoking status, we have used same categories as in the English analysis. Next slide, please. So using harmonized data, we were able to produce same results for the Welsh cohort. For example, here we see hazard ratios for combined arterial event at upper plots from left to right overall result, then stratified by sex and age group. And lower plots show hazard ratios for combined venous events stratified in the same way as the arterial events. I think that's it from me. Thank you, and back to you, Sam.
Thanks, Hoda. So the plan going forward is to wrap up and submit and preprint this very soon, God willing, because we've been saying this for ages. And given that like now most of the population is vaccinated, people might be interested in these analyses being done within the vaccinated population. So that's one avenue we might go down. And it will also be very interesting to look into how COVID diagnoses might enter CVD risk prediction models in the long term. So this is where we're going next. So thank you very much. And